We should be good to go. So hi folks, I'm Ankit. Right now I'm a blockchain engineer at Polygon, and I along with a couple of other people built a feature called gas swap, right? So basically what I kind of want to tell you guys is how we kind of built it and why we needed to do it. So essentially the entire idea is just essentially leveraging meta transactions to kind of improve user experience. Um, so in case some of you are new to Polygon, it's essentially an EVM compatible blockchain. It was founded in 2017, and essentially our mission from the get-go has been to essentially scale Ethereum. You might have heard now we have more chains that are going to be launched in a couple of months or years. So Hermes, Maiden, Zero, all of these chains, which are ZK rollups, will be coming soon. So like, for example, we have 3,000, more than 3,000 apps. We have around 7 million transactions happening daily, 60 million unique user addresses, and a 12 billion plus market cap. And we have a 2-second block time, which actually makes gaming a very lucrative decision on our blockchain. And so essentially, if you want an EVM friendly experience and a fast blockchain, which is cheap and works for everyone, that's essentially what Polygon is for. Now let's get back to what I actually want to talk to all of you guys about, which is essentially the gas swap feature. And I think the first question that we should have is like, why did we need this feature, right? Why was this feature built in the first place? So essentially what we were doing before is that every new user who had essentially no Matic could receive certain tokens, a certain amount of tokens, airdrop to their wallet automatically if they had never had any balance before. And after a certain point of time, you have to realize that for a token that has limited supply, so to say, since it's a fixed supply token, and there's some infrastructural costs as well, you kind of have to start thinking about how does this scale to the next billion users, right? Because that's essentially our goal, a blockchain that everyone can use. And that is when we kind of came up with gas swap, which uses something called meta transactions to essentially something that already exists, and we kind of put it into a ready-made solution where people can actually get Matic tokens for assets they already have without actually having to pay for it with actual gas, right? So the issue is that if you want to use the blockchain for the first time, you will not have ETH or you won't have Matic, right? And so that kind of results in a bad UX where people who kind of want to use it can't use it. And that also means that if you're a first-time user and you kind of want to use the network, and then let's say you have some USDC or maybe you have some WETH, and you're just angry, like you want to use it but you can't, right? So like certain other chains have different solutions for this. The most common is the airdrop approach that we had previously. Then you could also do a strategy such as airdrop users that active on other chains, sort of a vampire attack, which I guess no one has tried, but it's feasible. And I guess another solution, which I think Phantom does, is you can run a faucet that essentially drips gas on some predefined metrics that you kind of define. And so essentially, we kind of just changed this entirely with gas swap, which essentially allows you to bridge your other assets, and then you can actually get Matic tokens, any amount of Matic tokens as a way of using the network and using those assets that you already have, right? So this flowchart kind of just explains how it works, and I'll just walk you through it. This is kind of going to be kind of technical. Sorry about it. I didn't probably think about it that much, but so essentially what we have is a 0x API that kind of serves as the data. So let's say we can have the buy token, we have the sell token, we have a buy amount, and we have the slippage. And essentially from the API, we get the call data for the 0x proxy. And then we have our own gas swap contract, where we can essentially pass in the 0x approval address and any arbitrary bytes that we want. And this is the first step to kind of formulating the meta transaction, where we encode this fill quote function data or whatever we want to call the 0x proxy with as a Ip712 meta transaction. So we add things like the from data, the contract nonce, and the chain ID as a way to ensure that these transactions or meta transactions can't be replayed. So that kind of ensures security as well. And so like if you ever use the feature, you're going to notice that you kind of have to sign certain payloads, so to say, which is using the ETH sign typed data v4 RPC call, which is essentially what we are doing is we're providing the meta transaction data to the MetaMask wallet in the form of a structured data type, which is what EIP712 is all about. And so after you sign the data, you can essentially have the VRS of the signature, then you have the function data. And then we can call the main function, which is the execute meta transaction. And this is our function in the contract that essentially checks that the signature and the function data you're providing is actually accurate, and it works exactly as it's supposed to be. So we check that the signature is valid, we check that it does not call itself, and we then increase the contract nonce to ensure that you cannot replay the meta transaction. And ultimately what happens is whatever data that you supplied, so in this for encode function data step, it calls the function with, it calls the contract with that data. So it's like a normal transaction happening at that point of time, except obviously it's happening in the execute meta transaction. And then we return the control to the fill code function, which then calls the 0x proxy with the call data that we got from the API. So due to the way that the Matic token is essentially like a balance, so it's like an EVM compatible, or like an EVM balance, so to say. The way we need to kind of deal with it is different from typical ERC20 tokens. So we also perform some additional validation, such as we check if the output token is Matic. And then if we check that the return amount is always more than the expected amount. So if you remember that we took some slippage into account, right? And that is to ensure that it's like, let's say that you get arbed, the entire transaction reverts, and you kind of don't have a loss. And so now, like going back to the 0x proxy, you have this another function called the transform ERC20. This is where the 0x logic of it happens, where it's essentially a liquidity aggregator, right? So what we do is we provide a series of transformations to the tokens. So it's essentially a way of telling the contract that your DAI will now become ETH, your ETH will now become Matic, or so to say, like whatever the order is. It's a way of forming the order, so to say. And then the swap gets performed in the contract context, which is the gas swap that's all contract. And whatever tokens that we get from the 0x proxy, we just give it all to the user. And that's our automagical but slightly complicated way of making gas swap work. Now let's talk a bit about what meta transactions are in the first place and why we need to use it. So just talk of the Ip712 standards. Essentially, it's a Ethereum type structured data hashing and signing. So typically what the standard kind of defines is a way for you to kind of sign data and have it parsed by contracts in a way that it can perform actions in the user context. So now some things are part of the standard and some things aren't. Like, for example, we have added something like a contract nonce. This doesn't necessarily need to be part of the standard, and it isn't. But let's say that your encode data or the transaction data includes it, it is possible. Like, for example, like you can see in our case, we have the transaction data as the from address, the contract nonce, and the data that we want to be called in the contract context. In a different contract, maybe they do not want the from address, maybe they only want the to address, or maybe they don't want the nonce, maybe they want the expiry time. And this is what kind of allows like a dynamic sort of usage, that you can have different forms and different ways of making meta transactions work, and not just one thing. So EIP712 is more about structured data hashing and signing than actual meta transactions. So what EIP712 is actually like the foundational base on which we kind of make it work. Now going back to what EIP712 has, it's so like typically, since it's a typed message, we need to add a message like the Ethereum sign message that prevents collision with other signed data, like a normal transaction that you'd sign it, right? And you can also add type hashes like that essentially prevent like two different functions from being called. And finally, what we have to kind of separate two different things, two different dApps, is what we're calling a domain separator. And this is essentially what happens is that, let's assume a case where your function type hash is the same, you have added the typed message like this, and you have the transaction data that is also the same. What if a dApp could kind of copy other dApp's data, and that is essentially why you need a domain separator, where let's say you have the Aave app and you have another app which is the Uniswap app, and essentially, since the fact is that in the UI you're going to see them as different dApps or domain separators being shown in the UI, so you cannot spoof other domain messages, and that kind of prevents signature collisions as well, since that serves as a distinction between two similar meta transactions. So this is the kind of the code aspect of how we make EIP712 work. So if you remember, if you go back to the execute meta transaction function call, you typically have something like the user address, you have the function signature, and then you have SIGR, SIGS, and SIGV, right? What we do first is to kind of transform it into a struct, like a meta transaction. So if you remember from before, we have the nonce, we have the from, and then we have the function signature. Then we encode it with the data that you just saw, and then we get the meta transaction type hash. And this is the meta transaction type hash that I was talking about. This kind of prevents with the function signature collision, so to say, since the function name will typically be different in other cases, right? And then this hash is what we use to kind of, if you remember, the user also provides us the RS and V. And then using the VRNS and using the hash meta transaction, we can use EC recover and solidity to get the decoded address of a particular user. So basically, by getting the actual signature and by getting the VRS, we can decode the address using ECDSA. And then we also have the user address from before, which is provided to the function. And then we just perform a simple check that if the address does match, then we accept that meta transaction. And if the address doesn't match, then we reject it. And that is essentially how we are using it in our contract, so to say. Truth be told, the IP712 has a lot of depth to it that is more than what we are kind of utilizing here. But that's because our usage is kind of meant to be different, since it's more about enabling meta transactions and less about structured signing. And this is where we kind of come to the last part of what I want to talk about today, which is talking about transaction relayers and why we use them. So now a very good question is, why would you want to use relayers, right? And I guess the most basic reason is that you don't need to do it yourself. The drawback that comes from doing these transactions yourself is that you're going to have the added cost of storing all those private keys safely. And then you're going to have the added cost of managing nonces or managing those transactions, which is kind of problematic. And if you kind of want it to scale, it gets annoying really quick. And that is from my own experience as well. And also another thing is that most blockchains now, right, which have any amount of usage, let's say, let it be Ethereum or Polygon, they all have dynamic gas fees that kind of change from time to time and depending on network congestion. And there is no fixed way to determine what is the correct gas price, right? So this means that if you're a dApp or if you are a service provider who kind of wants to use these transactions and you want to do it yourself, these transactions might get rejected. If the gas is too low, they might get dropped. They might get stuck as pending. And that is just really bad for UX. You just don't want that. And that is where kind of transaction relayers come in, where essentially you have Biconomy or have Infura ITX who are really good at doing this sort of stuff, where when you want to use meta transactions, they'll just relay it for you as long as you have the gas tank up to date, and that's pretty much it. And the reason this works now is because now we have the infrastructure to kind of automatically price transactions as needed. So like in the case of even if the gas fees are kind of very dynamic, they still have ways to kind of get around it. And let's say that transaction has not been mined for a fixed amount of time, then they will also perform speed ups as needed to ensure that it definitely gets mined at a certain point of time. And this is what kind of results in a very good UX, because ideally we do not want a case where transactions are repeated, or any case where transactions kind of are pending for a long period of time, because the throughput that we want is very high, right? So this is how a typical flow with Infura ITX works. It's pretty simple. So typically what we have is we have a backend that kind of adds Matic to the Infura ITX gas tank. And from before, we have the user signed meta TX, right? We kind of just abstracted away that flow before as just an execute meta transaction call. But there's this added step that happens here where we kind of send their meta TX to Infura ITX. So Infura ITX has their own kind of RPC calls. One of them is called relay send transaction. So essentially what happens is we use the Infura RPC to kind of send a request from our backend to the ITX contract, like it's like a meta transaction data. So we just provide whatever the data that we had So what we are giving them will be like the to address, which will be the gas swap contract, the data will be, which will be the user signed meta transaction, and then the gas that we want Infura to forward. And then we also provide a mode like fast or slow, and like we are just picking fast here because we want it to be fast. And essentially this goes as a signed transaction, and this is what we kind of send to the Infura ITX. And eventually what happens is that transaction that we have actually goes from the Infura ITX relayer to our gas swap sol, which executes that function call, which is essentially an executable transaction call, using the user signed meta transaction bytes that we had from before with the gas price that Infura ITX has kind of calculated, so to say. And assuming that it doesn't get mined, it's just going to retry that until it gets mined. And I think the fast mode has a 1 minute and 30 seconds kind of delay. So it just picks up the gas price if required. And also in that step, what happens is that the matic gets deducted from our gas tank. And that's pretty much how relayers work. To be honest, like this is just one example of relayer. Different relayers have different ways of doing it. But since we're kind of planning on using Infura ITX, this is a flow using that. And that's pretty much it. Thanks a lot for listening. Thanks a lot for understanding how gas swap works, folks. If you want, you can give us a follow at 0x Polygon and myself at QEDK_. And that's pretty much it. Thanks a ton.
Thank you so much, Ankit. We do have a couple questions. There's a question about, and thank you, EG, for answering some questions. Check that out, everybody. There are some answers on there that we're helping you with if we don't get to it up here. A question about, will ETH2 be more powerful than Polygon? That's coming in from Yogenth. Am I saying that right? Does that make sense?
To be more powerful than Polygon.
Yes, it's a kind of vague
question. It's a common question that we get, but honestly, I'm not sure of how to answer that, because it's like, as we've kind of established many times before, is that we don't believe ourselves to be adversarial to Ethereum. We believe that we are firmly centered on Ethereum. And also the fact is that we have rollups, ZK rollups and optimistic rollups in the works that will eventually use the security of Ethereum. So if anything, I believe that it'll be more of a collaboration than who has more power, I guess. Yeah.
Right. That makes sense. And a question coming in from Gustavo is, obviously scalability is vital for the blockchain's future. Do you think that there's going to be L3 solutions basically for developers, or are there already solutions in mind to accommodate this scaling need? Also, what about data storage?
Yeah. That is a very good question. So essentially, we are seeing this come into like more solutions come into the space. For example, like that's the exact reason we kind of came up with Polygon Avail, which is a DA solution. And I guess the ideal world would be where we have ZK rollups and then you have DA solutions available, which are like in parallel. But yeah, like in an ideal world, yes, we will have L3s.
Nice. All right. Well, we're going to hop over. Thank you so much, Ankit. And like he said, you can reach him on the contact him on Twitter and also the resources he mentioned.